What if everything in the universe is moving farther away right now? The universe is not static, but constantly expanding beyond imagination itself. This discovery changed how scientists understand space, time, and existence completely. Galaxies are drifting apart like dots on an inflating cosmic balloon. This expansion was first observed through distant light-shifting redwards. That redshift showed galaxies were moving away from Earth consistently. The farther a galaxy is, the faster it seems to move. This strange relationship shocked astronomers when it was first discovered. It suggested the universe had a beginning point long ago. That beginning is now known as the Big Bang Theory. From a single point, everything began expanding into vast space. Space itself is stretching, carrying galaxies along with it. This means galaxies are not flying through space randomly. Instead, space itself is growing and creating more distance. Imagine dots on a balloon moving apart as it inflates. That balloon analogy helps visualize cosmic expansion more easily. But the universe has no edge or center, like a balloon. Every point in space sees other galaxies moving away. This makes the expansion uniform from every possible observation point. Scientists use powerful telescopes to study distant galaxies carefully. These observations help measure how fast expansion is occurring. Surprisingly, expansion is not slowing down, but accelerating over time. This acceleration puzzled scientists and led to new theories. One explanation is a mysterious force called dark energy. Dark energy is believed to push space apart continuously. Yet no one fully understands what dark energy actually is. It remains one of the greatest mysteries in modern science. The universe contains mostly dark energy and dark matter combined. Ordinary matter makes up only a small fraction of existence. Everything we see is just a tiny part of reality. Expansion means the universe will look very different in future. Distant galaxies may eventually become completely invisible to us. Light from them will take longer to reach Earth. Some galaxies are already disappearing beyond observable limits today. This creates a changing map of the night sky over time. Future civilizations may see fewer stars than we do now. That idea changes how we understand our place in universe. We are living in a unique moment in cosmic history. Astronomers call this the era of observable universe visibility. Eventually, only nearby galaxies may remain visible to observers. The rest will drift beyond detection forever in space. This makes studying expansion extremely important for scientific understanding. It also raises philosophical questions about existence and time. If everything is moving apart, what does that mean for us? It suggests the universe is dynamic and constantly evolving structure. Nothing in space remains truly permanent over cosmic timescales. Even galaxies themselves will eventually change or disappear completely. This idea challenges our sense of stability in reality. Humans are witnessing just a small snapshot of cosmic evolution. Billions of years before us, the universe looked different. Billions of years after us, it will change again. Expansion connects our present moment to infinite cosmic timeline. It reminds us how small our planet truly is. Yet it also shows how vast and fascinating existence can be. Every discovery about expansion deepens our curiosity about cosmos. Scientists continue measuring cosmic distances with increasing precision tools. These measurements refine our understanding of universal expansion rate. The rate of expansion is called the Hubble constant, named after astronomer Edwin Hubble, who discovered galaxy motion evidence. His work changed astronomy forever and reshaped modern cosmology. Today, telescopes continue building upon his groundbreaking discoveries. Each observation brings us closer to understanding universe behavior, yet many questions remain unanswered about cosmic expansion forces. The universe still holds secrets beyond our current understanding, and this mystery continues to inspire scientific exploration today. The expanding universe raises deeper questions about the origin of everything. Scientists believe all space, matter, and time began from singularity. This singularity was infinitely small, hot, and extremely dense initially. From that point, expansion began shaping the cosmos we see. Early universe was filled with energy, not stars or galaxies. Over time, cooling allowed particles to form simple atoms. These atoms later combined to create stars and galaxies slowly. Gravity pulled matter together, forming massive cosmic structures gradually. Without expansion, galaxies would never have formed as they exist. Expansion created space needed for cosmic structures to evolve. The universe is not expanding into empty space outside it. Instead, space itself is continuously stretching in all directions. This concept is difficult to imagine for human minds. We naturally think of expansion as movement inside a space. But in reality, space and time are both expanding together. This means distances between all galaxies are increasing constantly. Even atoms remain unaffected because forces hold them tightly together. Expansion mainly affects vast, empty regions between cosmic structures. The universe is becoming larger every single second continuously. Scientists measure this expansion using light from distant objects. When light stretches, it becomes redder, called redshift effect. This redshift provides strong evidence for universal expansion theory. Without it, we would not understand cosmic movement today. Different galaxies show different speeds of separation from us. This variation depends on distance and space stretching rate. The farthest galaxies move away faster than closer ones. This relationship helps scientists map the universe's expansion structure. Expansion suggests the universe had a definite starting point. That idea challenges ancient beliefs about eternal static cosmos. Modern cosmology supports a universe with beginning and evolution. This beginning event is known as the Big Bang theory. The Big Bang was not an explosion in space. It was expansion of space itself from extreme density. Everything we see today originated from that early state. Even time began at that initial moment of expansion. This means before expansion, traditional time may not exist. Such ideas challenge our understanding of reality itself deeply. Scientists use mathematics to describe how expansion behaves today. These equations help predict future behavior of the universe. Observations confirm that expansion rate is not constant. Instead, it appears to be accelerating over time now. This acceleration suggests presence of unknown cosmic force. That force is called dark energy by scientists worldwide. Dark energy acts like invisible pressure expanding space outward. However, its true nature remains completely unknown still today. Understanding it is one of science's biggest challenges currently. Expansion affects how we perceive distance and timescales. It changes our understanding of cosmic history significantly. Light from distant galaxies shows universe's past conditions. We essentially look back in time when observing space. This makes astronomy a study of history itself. The further we look, the older the light becomes. This gives scientists a timeline of cosmic evolution. Expansion is key to understanding that cosmic timeline fully. Without it, universe would be impossible to explain scientifically. It connects physics, astronomy, and cosmology into one system. Every discovery adds more detail to this expanding picture. Yet many mysteries still remain unsolved in cosmology today. The universe continues to surprise scientists with new findings. Expansion may hold answers to existence itself eventually. It may explain fate of everything in future time. Our understanding is still growing with each new observation. Technology helps us explore deeper into expanding universe. But questions often grow faster than answers discovered. The mystery of expansion continues to challenge human knowledge. The accelerating expansion of the universe remains a shocking discovery today. Scientists expected gravity to slow cosmic expansion over time. Instead, galaxies are moving apart faster than ever before. This unexpected acceleration changed modern cosmology completely and permanently. It suggests an unknown force dominates the universe's behavior. This force is what scientists call dark energy. Dark energy makes up most of the universe's total content, yet it cannot be directly seen or detected easily. Its existence is inferred only through cosmic observations. Expansion measurements show galaxies drifting apart at increasing speed. This contradicts earlier expectations about gravitational slowing effects. Scientists now believe dark energy counteracts gravity on large scales. However, its exact mechanism remains completely unknown still. Many theories attempt to explain dark energy's mysterious nature. Some suggest it is a property of empty space. Others believe it involves unknown particles or quantum effects. None of these explanations have been confirmed experimentally yet. Understanding dark energy is key to understanding expansion fully. Without it, cosmic evolution cannot be properly explained. The universe may eventually expand forever due to this force. This scenario is known as the Big Freeze theory. In that future, galaxies drift too far apart forever. Stars will slowly burn out over billions of years. Eventually, darkness may dominate the entire universe completely. This idea creates a chilling picture of cosmic destiny. However, this outcome depends on current expansion rates continuing. Scientists are still refining measurements of this acceleration today. Tiny errors in data can change cosmic predictions significantly. Space telescopes play a major role in these studies. They observe distant supernovae to track expansion speed accurately. Supernova explosions act as cosmic distance measurement tools. These bright events help map universe expansion history clearly. Each observation improves our understanding of cosmic behavior, yet uncertainties still remain in key measurements and models. Expansion also affects how we view the universe's size. The observable universe is limited by speed of light. Light from very distant regions has not reached us yet. This means there are parts of the universe we cannot see. As expansion continues, more regions move beyond visibility range. Eventually, distant galaxies will disappear from observation entirely. Future astronomers may see a much emptier sky than today. This makes our current era scientifically very important. We are able to observe more cosmic history than future observers. This is sometimes called the golden age of cosmology. Expansion helps scientists understand how the universe evolves over time. It connects early universe conditions with present-day structures. Galaxies, clusters, and voids all result from expansion processes. Without expansion, cosmic structure would not exist as it does. Matter distribution depends heavily on early expansion dynamics. Tiny fluctuations grew into massive galaxies over billions of years. Gravity shaped these fluctuations into structured cosmic networks. Expansion provided the space for this evolution to occur. The universe is therefore both structured and dynamic simultaneously. It is constantly changing on scales beyond human imagination. This continuous change defines modern understanding of cosmology. Every second, space itself grows larger than before. We are literally living inside expanding space-time itself. This concept challenges everyday intuition about reality completely. Scientists continue refining models to explain these behaviors better. New discoveries frequently adjust our understanding of expansion dynamics. The universe still holds unanswered questions about its future. Expansion may determine ultimate fate of everything in existence. Understanding it is essential to understanding cosmic destiny itself. Humanity is still uncovering layers of this vast mystery, and each discovery brings us closer to cosmic truth. The expansion of the universe also reshapes our idea of time itself. Time and space are deeply connected in modern physics theories. This relationship is described through Einstein's theory of relativity. According to it, space and time form a single fabric. This fabric is known as space-time in scientific language today. Expansion stretches this space-time fabric across the entire cosmos. As space expands, the distances between objects increase continuously. This affects how we measure cosmic time and distance. Time itself behaves differently in extreme gravitational environments. Near massive objects, time moves more slowly than elsewhere. This shows time is not absolute, but relative in nature. Expansion does not directly speed up or slow down time, but it changes the structure within which time exists. This makes the universe dynamic in both space and time. Understanding space-time is essential to understanding cosmic expansion fully. Without this concept, expansion would be impossible to explain scientifically. The universe is not expanding into empty external space. There is no outside boundary or edge to the universe. Instead, space itself is continuously creating new distances. This idea is difficult but central to modern cosmology. Every galaxy participates in this expansion equally overall. There is no single center of expansion in space. Every point in the universe appears to move outward. This creates the illusion of a central explosion point. But in reality, expansion happens everywhere, simultaneously. The universe is uniform on very large cosmic scales. Scientists call this property the cosmological principle. It suggests the universe looks similar from every location. This principle helps simplify complex cosmological models significantly. However, local structures like galaxies break this uniformity. Gravity binds matter together in small regions strongly. These structures resist expansion on smaller scales effectively. That is why atoms and planets do not expand. Only vast cosmic distances are affected by expansion. This difference creates an interesting balance in nature. Local stability exists within global cosmic expansion simultaneously. Expansion also influences how we interpret cosmic history. Looking at distant objects means looking into the past. Light takes millions or billions of years to travel. Therefore, we see ancient versions of galaxies far away. This makes space a natural time machine for scientists. Expansion increases this effect by stretching light further. Redshift of light reveals how far galaxies have moved. Greater redshift means faster recession from our viewpoint. This helps scientists estimate age and scale of universe. Expansion history is reconstructed using these observations carefully. Different periods of expansion reveal different cosmic eras. Early universe expanded extremely fast after its beginning. This rapid phase is called cosmic inflation theory. Inflation explains uniformity seen in universe today. It also explains small fluctuations that formed galaxies later. Without inflation, universe would look very different now. Expansion continues today, but at a slower rate. Yet recent data shows acceleration is increasing again. This shift suggests unknown physics still at play. Scientists continue searching for deeper explanations behind it. New experiments aim to measure expansion more precisely. Space missions help gather detailed cosmic data constantly. These missions expand human knowledge beyond Earth's limits. Each discovery refines our understanding of universal structure. The universe remains a constantly evolving system of change. Expansion is key driver of this cosmic evolution process. It shapes everything from galaxies to empty space itself. Our understanding is still incomplete, but rapidly improving, and space-time continues expanding beyond our full comprehension. The future of the universe depends strongly on its expansion rate. Scientists study expansion to predict ultimate cosmic destiny carefully. Several possible outcomes exist based on current scientific models. One possibility is endless expansion continuing forever into darkness. In that scenario, galaxies drift apart until isolation dominates. Stars eventually burn out, leaving a cold universe behind. This is often called the heat death of universe. Energy spreads so thin that no new structures form. Life as we know it would become impossible eventually. Another theory suggests expansion might slow down over time. If gravity becomes dominant, universe could reverse its expansion. This reversal is called the Big Crunch scenario. In that case, everything would collapse back into dense state. Galaxies would move closer together instead of apart. Temperature and density would increase dramatically during collapse. Some models even suggest cycles of expansion and collapse. This idea is known as cyclic universe theory. It proposes Universe goes through endless repeating phases. However, there is no strong evidence yet supporting cycles. Current observations favor continuous accelerated expansion instead. This makes dark energy extremely important in cosmic fate. If dark energy remains constant, expansion continues forever. If it changes, universe fate could also change dramatically. Scientists are actively measuring this possibility through observations. Tiny differences in data could reshape cosmic predictions. Space telescopes help collect precise information about distant galaxies. Supernova studies provide insight into expansion history over time. These exploding stars act as standard distance markers in space. They allow scientists to calculate how fast universe expands. Observations consistently show acceleration across different cosmic regions. This strengthens belief in dark energy's influence everywhere. However, its origin remains completely unknown still today. Some theories link it to vacuum energy in space. Others suggest modifications to gravity itself on large scales. Neither explanation has been confirmed experimentally so far. Understanding this mystery is one of physics' biggest goals. Expansion also influences how we understand our cosmic future. It determines how visible universe will change over time. Distant galaxies will eventually disappear beyond observational reach. Future skies may appear much emptier than today. Only local galaxy clusters may remain visible eventually. This creates isolation between cosmic structures over time. Humanity's perspective of universe will dramatically change. Future observers may not see evidence of expansion easily. That makes current observations extremely valuable scientifically. We are living in a rare observational era. This era allows us to study expansion clearly. Cosmologists rely on this moment to build models. Expansion also influences philosophical ideas about existence. It raises questions about purpose and scale of reality. Humans begin to realize their small place in cosmos, yet they also seek connection to universal processes. We are part of expanding space-time itself. Our atoms were formed inside ancient stars long ago. Those stars existed because of earlier cosmic expansion. Everything in existence is linked through this process. Expansion connects past, present, and future of universe. It is not just motion, but creation of space. This makes it one of most profound scientific ideas. It reshapes how humanity understands reality itself deeply. Each discovery brings new questions about cosmic destiny. Scientists continue refining models with better technology, yet universe still hides many unanswered mysteries today. Expansion remains central to understanding everything we observe, and its story is still unfolding across time. The expanding universe ultimately reshapes how we understand our existence. It shows that nothing in the cosmos is truly permanent. Even galaxies themselves are slowly drifting apart over time. This constant change defines the nature of reality itself. Humanity exists within a universe still actively evolving today. Every moment, space is stretching beyond previous limits. This expansion is invisible but profoundly powerful in effect. It influences the entire structure of everything we observe. From stars to empty voids, everything is affected. Yet we experience no direct feeling of this expansion. That is because local forces hold matter tightly together. Gravity and electromagnetism dominate on smaller scales near us. Only vast cosmic distances reveal expansion clearly to observers. This makes the universe both familiar and strange simultaneously. We live in a stable environment inside a dynamic cosmos. Understanding expansion helps us appreciate the universe's complexity deeply. It also highlights how much we still have to learn. Science continues to explore this expanding cosmic mystery daily. Each discovery brings us closer to deeper universal truths, yet new questions always emerge with every answer found. This endless cycle drives scientific curiosity and exploration forward. Expansion also affects how we think about time itself. Time and space are intertwined within the fabric of reality. As space expands, our cosmic perspective shifts gradually. This changes how we interpret past and future events. We are essentially observing a living, changing universe constantly. The night sky we see is not static history. It is a snapshot of ongoing cosmic evolution. Distant light tells us stories from billions of years ago. These stories reveal how the universe has transformed over time. Expansion ensures that change is fundamental to cosmic existence. Nothing remains exactly the same on universal timescales. Even atoms were once formed in ancient stellar explosions. Those stars existed because of earlier stages of expansion. This connects all matter through a shared cosmic origin. We are literally made of ancient stardust spread across space. Expansion is responsible for shaping this cosmic distribution. Without it, structure and universe would not exist. Galaxies, stars, and planets all depend on expansion history. It is the foundation of cosmic structure formation itself. Future expansion will continue shaping universe destiny ahead. Whether it ends in freezing or endless expansion remains unknown. Scientists still debate final fate of the universe today. Observations suggest accelerated expansion will likely continue indefinitely. This would lead to increasingly isolated cosmic structures. Eventually, galaxies may become unreachable from one another. The universe could become dark, cold, and extremely quiet, but these predictions depend on current understanding of physics. New discoveries could completely change these conclusions in future. That uncertainty is what makes cosmology so exciting. Expansion teaches us humility about our place in cosmos. It shows how small yet connected we truly are. We are observers within an expanding cosmic story. Our understanding grows as the universe continues evolving. Every scientific step reveals deeper layers of reality. The universe remains larger than human imagination can grasp. Yet we continue striving to understand it fully. Expansion is not just a concept, but a reality. It defines existence from smallest particles to largest galaxies. Our journey of understanding has only just begun. The cosmos still holds countless mysteries waiting to be discovered. Future science may reveal answers we cannot imagine today. Expansion will continue shaping those discoveries endlessly forward. Humanity's quest to understand the universe will never truly end, and the expanding universe continues silently writing its story.